Welcome back, everyone. I'm Jordan Giesecke, and this is The Limiting Factor. Idra Group, which pioneered the Gigacasting machines that Tesla uses for their massive underbody castings, is now working on giga-scale machines for chip-cast magnesium, also known as Thixomolded Magnesium. This matters because die-cast magnesium parts weigh roughly a third less than die-cast aluminum parts. The question is, what is Thixomolding? Today I'll answer that question along with how it compares to other casting technologies and the engineering challenges that Idra and their partners had to solve to make Thixomolding work for large castings. Before we begin, a special thanks to my Patreon supporters, YouTube members, and Twitter subscribers, as well as Rebellionaire.com. They specialize in helping investors manage concentrated positions. Rebellionaire can help with covered calls, risk management, and creating a money master plan from your financial first principles. First, for those concerned about the flammability or corrosion characteristics of magnesium, I'd recommend watching the first video of the magnesium series linked in the card above. In short, the flammability and corrosion concerns around magnesium aren't the primary challenge for the adoption of magnesium for vehicle structures because they're solved problems. The primary challenge is actually size limits on high-quality mass-produced castings, and cost and availability. In this video and the next, I'm tackling the challenge of large, high-quality mass-produced castings, and in a subsequent video on Magrathea, I'll cover cost and availability, as well as how magnesium can be produced with net zero emissions. To understand what magnesium thixomolding is, let's start with familiar territory. The gigacasting process Tesla uses for aluminum, which I'll just call gigacasting for short, and go from there. With gigacasting, the molten aluminum is held in a crucible near the casting machine, ladled into the shot sleeve, and then injected into the die at high pressure. Besides the high injection pressure, the die is also under vacuum to reduce trapped air in the cast part. That's important because trapped air leads to porosity, which can reduce the quality of the cast part. Next, the molten aluminum is rapidly cooled using large banks of thermal management units. After the metal solidifies, the casting is removed and then trimmed. With magnesium thixomolding, the first difference is of course the metal used. When magnesium is in its molten state, there's a risk that under the right conditions, it can react with oxygen in the surrounding air and start on fire. That reactivity varies a lot depending on how hot the molten material is, whether it's pure magnesium or an alloy, and the surface area to volume ratio of the magnesium. That is, it's not a major issue with good processes, but it's still a risk for casting magnesium that aluminum doesn't have to the same extent. Thixomolding levels the playing field and effectively eliminates the reactivity and ignition risks of magnesium. How? The injection chamber is connected to a hopper that holds chipped magnesium. It houses an auger, and it's surrounded by an array of heating elements. The magnesium chips from the hopper are compressed and conveyed by the auger and heated by the heating elements until they become a slurry that contains both molten magnesium and solid magnesium, like shaved ice in water. That slurry is in what's called a thixotropic state, which is how thixomolding gets its name. It's a molding process that uses a thixotropic liquid. We don't need to get into what a thixotropic liquid is today. The key point is that we're talking about a viscous or slow-flowing metal slurry that's only partially molten. As a side note, the viscosity of the slurry can vary quite a bit depending on the ratio of solid to molten metal. It can range from the consistency of warm butter to solid enough that it can form slugs for injection into the die. Getting back on track, the thixomolding process limits the reactivity of the magnesium with the oxygen in the air in 4 ways. First, magnesium doesn't become reactive with air until it's molten, and the hotter the molten metal, the more reactive it is. With thixomolding, the magnesium is in a semi-molten state, which means only a fraction of the metal is molten and reactive, and the metal that is molten is cooler than the metal that would be used with a fully molten process. Second, argon gas is often used in the hopper to displace oxygen. Argon is inert and it's not a greenhouse gas, and it's used in a sealed chamber so it's less of a concern than cover gases, which I'll cover in a moment. Third, even if argon wasn't used, the air between the magnesium chips is forced out by the compression of the auger before they even reach a temperature where they might react with oxygen. Fourth, when the magnesium is injected into the die, just like with gigacasting, the die contains no air because it's under vacuum. After the magnesium cools, it's then removed and trimmed for use in a vehicle. So end to end, with Thixomolding, molten magnesium is never exposed to oxygen, which eliminates flammability risks in confined spaces like factories. On that note, Thixomolding is easily confused with Rheocasting. Rheocasting is short for rheopectic casting. Rheopectic, in this case, is again just another word for the semi-molten metal used in the casting process. Technically, a rheopectic liquid is different than a thixotropic liquid, but for the purposes of today's video, the characteristics of the two liquids is the same. They're both liquids that contain a suspension of solid particles, or slurries. What differs and what matters is the process involved in casting them. With Rheocasting, the process is very similar to Gigacasting. The metal is heated until it's fully molten in a crucible near the casting machine, but because it's magnesium, this time a cover gas is used in the crucible. A cover gas is a heavy inert gas that sits on top of the molten metal to protect it from reacting with the surrounding air, and it also reacts with the surface of the molten metal to form a protective film. At some point between being melted in the crucible and transferred to the shot sleeve, the metal is cooled to a semi-molten state. There are two ways that can be done. The first is to ladle the metal from the crucible to a cooling unit, where it's formed into a slug for injection into the die. The second is to cool the metal in the crucible to a semi-molten state, and then pump it into the injection chamber with a transfer tube. After the metal is transferred to the injection chamber, it's injected into the die, the metal is cooled to its solid state, and then it's removed for trimming. The Rheocasting process creates a number of challenges and disadvantages. First, the most commonly used cover gases for Rheocasting are SF6 and SO2, which are sulfur hexafluoride and sulfur dioxide. These gases are non-toxic, but because they can displace air and therefore oxygen, they do pose an asphyxiation risk to workers in confined spaces. That's a small risk when managed properly, but a risk nonetheless. Additionally, sulfur hexafluoride is over 23,000 times more potent as a greenhouse gas than CO2. Sulfur dioxide isn't a greenhouse gas, but it is a severe irritant to the lungs and eyes. Second, because the magnesium is heated to a higher temperature and then cooled to its semi-molten state, rather than being heated just enough to partially melt the metal like Thixomolding, Rheocasting uses more energy and wastes more of it than Thixomolding. Third, with the ladle method, there's a brief period of time where the molten metal is fully exposed to air. That's a fire hazard, one that can be controlled with good processes, but it still adds additional risk. Despite the challenges of Rheocasting, it does offer one primary benefit. After the parts are cast and trimmed, the scrap can be directly recycled by throwing the scrap metal back in the crucible and remelting it. That's as opposed to the Thixomolding process, where the trimmings have to be melted, formed into ingots, and then re-chipped before being put back in the hopper and melted again for casting. So overall, Rheocasting and Thixomolding are comparable processes, but Thixomolding is a safer process because the molten magnesium is never exposed to air and it doesn't require a cover gas, which is generally either a potent greenhouse gas and/or an additional human hazard in confined spaces. Those are likely the primary reasons why Idra decided to pursue a Thixomolding process for magnesium casting rather than Rheocasting. With that said, in my view, another potential reason is the simplicity. With Rheocasting, the molten and semi-molten metal is handed off or transferred between different machines or different parts of the casting machine, whereas with Thixomolding, everything happens within the injection chamber. That should allow for continuous temperature monitoring from chipped metal to the final cast part. Why does temperature control matter? Because for semi-molten metal, small changes in temperature can have a big impact on the liquid-to-solid ratio, which affects its flowability during injection. Flowability has a big impact on the ability of the semi-molten metal to completely fill the die during injection and the porosity of the cast part. So temperature control is a big factor in quality control. On that note, earlier in this video and in the last video, I said that size limits on high-quality mass-produced castings were one of the factors holding magnesium back as a structural metal. Size limits is shorthand for a number of requirements that go hand in hand to make large magnesium castings that are commercially viable for mass-produced vehicles. Let's take a closer look. By size limits, I mean parts larger than 10 kilograms. By quality, I primarily mean low porosity, which makes for stronger and more ductile parts. And by mass-produced, I mean hundreds of thousands of parts per year. In the past, there wasn't a casting process for magnesium that could do all of these things at once. Some people might point out that Tesla's Gigacasting machines produce large, high-quality parts and at a high rate. Why not just swap out the aluminum for magnesium? That's a good point. Cold chamber high-pressure die casting machines like the Giga press can actually be used to cast magnesium by swapping out the aluminum in the crucible with magnesium and by using a cover gas. That's an oversimplification, but it's the general idea. Interestingly, the ability of gigacasting machines to cast magnesium is how Idra was able to design their Thixomolding machines as a bolt-on option for their gigacasting machines. That is, a company like Tesla could buy the Thixomolding unit, attach it to their existing gigacasting machines, and start producing Thixomolded magnesium castings. So again, if that's the case, why not just forego the expensive Thixomolding unit and just use fully molten magnesium with a gigacasting process? It's because casting parts with Thixomolded magnesium is superior to casting parts with molten magnesium. Why? Starting with the quality requirement, with Gigacast aluminum, when the aluminum is injected into the die, the pressure is so high and the molten metal is so flowable that the aluminum is essentially sprayed into the die. That creates turbulence that traps air and results in porosity. That's as opposed to viscous semi-molten metal that creates a laminar flow that's less susceptible to trapping air. That means that despite the fact that gigacasting machines use a vacuum to reduce the porosity of cast parts, Thixomolded parts have even lower porosity. Why does porosity matter? Low porosity can dramatically increase the strength and ductility of cast parts. The image on screen shows that of the casting techniques included in the plot, high-pressure die-cast parts have the lowest quality. Next is vacuum-assisted die casting, which I assume is the vacuum-assisted high-pressure die casting Tesla used for gigacasting, which has low to medium quality. Finally, semi-solid casting. Semi-solid casting encompasses Thixomolded and Rheocast parts, which have such high quality that they're competitive with forged parts. That's important for magnesium because it tends to be a weaker and less ductile metal than aluminum. So in order to make cast magnesium competitive with cast aluminum, Thixomolding is the best option. As a side note, with regards to the cost continuum shown on this slide, I'll take you deeper into that in the next video of the series. Next, as for speed, magnesium Thixomolding produces parts at a similar rate to aluminum gigacasting. For example, on screen is a comparison between a hot chamber die casting machine on the left and a Thixomolding machine on the right. I timed the Thixomolding machine at 44 seconds per cycle and the die casting machine at about 50 seconds, so the Thixomolding machine is a bit faster. Although the speed advantage that magnesium has here could, in part, be related to the size or complexity of the part being cast, I have confirmed with people in the industry that it's generally true that Thixomolding is typically similar in speed to gigacasting. Moving on to part size, up until a few years ago, the maximum part size for Thixomolding was less than 5 kilograms, and it was only in the last year that part size reached 10 kilograms. How was Idra able to increase the part size to 20 kilograms, and is 20 kilograms large enough for gigacastings? First, as I said a moment ago, Thixomolding requires precise temperature control for high-quality parts. But there's another reason why temperature control is important outside of quality. If the magnesium goes from being semi-molten in the auger to solid, it can destroy the auger, which, including downtime, can cost millions of dollars to replace. If Idra is increasing the size limit of Thixomolded castings, it means they've solved the temperature control challenge. My guess is with better electronics and control software. The second challenge for large Thixomolded parts was backflow. The auger not only conveys and compresses the magnesium chips, it acts as a piston to inject the shot into the die. So it has to be able to both rotate freely and create a tight enough seal to generate high injection pressures. Idra solved that by making the auger and the injection piston separate functions. The auger conveys the molten metal to an injection chamber. Then, as far as I can tell from the image, the auger moves forward to seal against injection chamber pressure at the tip of the auger, and the piston generates the necessary pressure to force the metal into the die. Idra calls this thixotropic piston injection, or TPI, and it should sidestep both the backflow issue and allow for much higher injection pressures and larger cast parts. While we're on the topic of injection pressures, it's worth noting that even though thixomolding requires higher injection pressures, it actually requires lower clamping forces for a given part size. Why? As I explained in my original Gigacasting video, the die is like a giant catcher's mitt, but in this case the baseball is a 60 kilogram slug of molten aluminum that's injected into the die at 22 miles per hour. That's why Gigacasting machines require massive clamping forces of over 6,000 tons, and they weigh over 400 tons. With thixomolding, the shot of metal is the consistency of soft butter rather than a liquid, which results in slower injection speeds, or a slower moving molten metal baseball, and therefore requires a smaller die or catcher's mitt for a given weight of material. The implication here is that gigacasting machines that companies like Tesla already use for aluminum should be large enough to cast full underbody castings made of magnesium, and that the limiting factor for casting size is Idra's ability to increase the injection pressure for the thixotropic piston injection process. Furthermore, for the same shot weight, magnesium can make a larger casting because it's a lighter metal. That means a 20 kilogram thixomolded magnesium casting is roughly equivalent to a 30 kilogram aluminum casting. For reference, the rear casting on the Model Y is about 65 kilograms, and for the front casting it's closer to 80 kilograms. So if Idra can double or triple the injection pressure of their thixotropic piston injection units, a company like Tesla should be able to manufacture full underbody castings with their existing gigacasting machines. As a final note, with all the benefits of thixomolding, why is Idra focused on thixomolded magnesium instead of thixomolded aluminum? My guess is that it's because magnesium has more to gain from thixomolding than aluminum does, and that's for two reasons. First, as we saw earlier, thixomolding solves the cover gas problem for magnesium, whereas aluminum doesn't require a complex injection system to avoid contact with oxygen in the atmosphere because it's not as reactive. Second, thixomolding gives the corrosive aluminum additional parts to corrode, which adds expense. What do I mean by that? Let's start by looking at aluminum gigacasting as an example. The molten aluminum used for gigacasting is more corrosive to the steel die than the semi-molten magnesium used in thixomolding. That's because the hotter the metal, the more reactive it becomes, and molten aluminum is much hotter than semi-molten magnesium. Additionally, even at similar temperatures, aluminum is more reactive with the die than magnesium. The result is that dies for thixomolded magnesium last about 2 to 3 times as long as they do for aluminum gigacasting. While it is true that with aluminum thixomolding that the aluminum would be cooler than it is with gigacasting, it would still be hotter than magnesium because aluminum's melting temperature is slightly higher than magnesium's. Furthermore, as I said, even at similar temperatures, aluminum is more reactive with the steel dies than magnesium. What all that means is thixomolded aluminum would chew through dies more quickly than thixomolded magnesium, but it would also have a new part to react with, the expensive steel auger that's used to convey the semi-molten aluminum to the injection chamber. That means higher maintenance costs. With that in mind, in my view, it makes more sense to use thixomolding with magnesium. That's because compared to aluminum, thixomolded magnesium will offer lower maintenance costs due to longer die and auger life and produce larger parts for the same shot weight, which should have equal or greater strength and ductility thanks to lower porosity. The only question is whether there's enough magnesium on the market at a low enough price to make thixomolded magnesium viable. In short, as I'll cover later in the series, currently magnesium is expensive and scarce, but that will change as the decade progresses. So Idra is positioning themselves well with their magnesium thixomolding gambit. In summary, at a high level, Thixomolded Magnesium uses the same high-pressure cold chamber die casting machines that Gigacasting uses, but it requires an injection system that can generate high enough pressures to inject semi-molten magnesium into the die chamber instead of fully molten aluminum. So Thixomolded Magnesium is a more difficult engineering challenge than aluminum gigacasting, but it's worth it. By using magnesium instead of aluminum and semi-molten metal instead of fully molten metal, it dramatically improves the quality of the cast part by reducing porosity, which improves the strength and ductility of the magnesium part while producing parts that are a third lighter. The challenges with magnesium meant that up until a few years ago, the size of Thixomolded magnesium parts were limited to less than 5 kilograms, and automotive use cases tend to require larger parts. However, that's changing with Idra's new Thixomolded piston injection units that can handle shot weights of up to 20 kilograms. And, in my view, the same way that gigacasting machines are now almost 2.5 times larger than the first machines that were introduced a few years ago, we'll likely see Idra offer much larger shot weights in the next few years for Thixomolding. So in the next video of the magnesium series, I'll go a level deeper to explore how Thixomolded magnesium would affect the manufacturing and design of castings compared to aluminum gigacastings, where they could be used and their advantages. If you enjoyed this video, please consider supporting the channel by using the links in the description. Also, consider following me on X. I often use X as a testbed for sharing ideas, and X subscribers, like my Patreon supporters, generally get access to my videos a week early. On that note, a special thanks to my YouTube members, X subscribers, and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.